So welcome to the members seminar. Today we're very lucky to have James Stone, who came all the way across campus from the School of Natural Sciences to speak to us about astrophysical fluid dynamics.
Great, so hopefully you see my full screen in presentation mode now. Great.
Great.
So thanks for the invitation, and it's a pleasure to be here. Of course, I would have much rather have done this in person, and one of the reasons for being at the Institute is being able to work with and interact with people in other fields, very easily, conveniently. But so I regret not being able to talk to individuals personally, but hopefully we'll have a chance in the future to chat more. And I thought I would just give you a higher level overview of fluid dynamics as applied in astrophysics. So this is going to be more of a general talk with lots of images and so on. Rather than getting into the technical details, I'm very happy to talk about those if anybody's interested. But I thought for this audience, you may not be familiar with how fluid dynamics might be applicable, and I try to give you a sense of that. So it's going to be a bit of a general talk and hopefully somewhat entertaining because we have great images in astrophysics. So I'm going to start with a motivation. Why would we think of trying to use fluid dynamics to describe astrophysical systems? I'll tell you a little bit about what mathematical models we use. We were already talking a little bit about compressibility versus incompressible, so it's a little bit more about that. I'm going to inevitably talk about numerical methods because they've become so important in this field in the last 10, 20 years. And I'll try to give you a sense of how this all works by talking about one particular application. I mean, these methods are used for all kinds of problems, but I'll talk about just one particular one, trying to understand accretion onto black holes and other compact objects, and finish up with some future challenges. I hope people would feel free to interrupt me at any time. It's a small group, so you can just speak up and I'll be happy to answer questions. So don't hesitate to interrupt me if something's not clear. So why would we want to think about fluid dynamics? Well, the reason is that essentially what we really need to be doing is plasma physics, because virtually all of the visible matter in the universe is a plasma. That includes stars, all stars in their interiors. They're basically self-gravitating balls of ionized plasma. Even evolved stars, compact objects like neutron stars and white dwarfs, those are sort of quantum plasmas where electron degeneracy pressure and neutron degeneracy pressure supports them. There's still fluids in their interior. And so even in those stages of evolution, they're basically plasmas. Virtually all of the material on planets is either liquid or a plasma, except for a few of the planets, the so-called rocky planets in the interior of the solar system, like the Earth. They have a very, very thin crust of solid material, which is very important to us. It's all of our lives and our existence depends on this crust. But in terms of the total mass content of not only the Earth, but also the solar system as a whole, this solid material is absolutely minuscule amount. And so it's a very, very tiny amount of solid material really anywhere in the universe. The other places, maybe in comets and asteroids, there's some solid material, but basically nowhere else in the solar system. And beyond the solar system, there's material between the stars, the so-called interstellar medium, it's a plasma, the intergalactic medium, the material out of which galaxies form and which permeates intergalactic space. All of this stuff is a plasma. Of course, most of the material in the universe is dark matter, which we have no idea what that is, but the stuff that we can see is a plasma. And I thought I would give you some examples just to bring this home of the kind of things that motivates this. Like, for example, the sun. So here's an ultraviolet image of the sun, and here's a very small segment which has been imaged with the Dekist solar telescope. It's actually an animation over a course of 10 minutes or so. Well, it used to be an animation when it was running before, but sorry, I'll try running that again. Well, unfortunately, I had a little problem with this movie here. It's here we go. There we go. It keeps stalling. I can't understand why this is doing this. But anyways, I'll show the first few seconds again. The point is you can actually watch convection occurring on the solar photosphere. So what these are convective cells. And the dark regions are plasma, which is a little bit cooler and sinking, and the bright regions are are a little bit hotter and a little bit brighter. And so you can actually watch convection boil away on the outer layers of the sun. About the outer 30% of the sun is convecting. And this is studied through, large-scale numerical simulations of people interested in trying to understand convective motions in the sun and other stars. This is an animation of the entropy fluctuations in a periodic box in solar conditions, and showing you, the downdrafts and the turbulence generated from this compressible convective motion. What you can't see is that if you look straight down on this computational box, the surface looks very, very similar, remarkably similar to what the solar telescope looks like. So you can reproduce the properties of convection in the sun through these fluid dynamical simulations and understand properties of the solar interior this way. In fact, the role of magnetic fields in the sun is also very evident just by looking. Now we're looking at ultraviolet images of the sun taken over the course of about a month from the Solar Dynamics Observatory. And you can see how plasma is confined to filaments by magnetic fields above the surface of the sun. You can see active regions which associate with sunspots. It's where magnetic flux is emerging from the photosphere. And these active regions are very active. They produce dissipation and heating of the coronal gas. They produce outflows and jets of material from which the solar wind emanates. And so it's pretty clear that the outer layers of the sun are completely dominated by magnetic fields, and that incorporating these MHD effects to understand the solar corona and solar wind is absolutely crucial. You wouldn't understand sunspots, for example, and flares without understanding the magnetic activity in the sun. So this kind of data immediately motivates astrophysicists to try to think about modeling stars as fluids, as fluid dynamical systems, especially including magnetic fields. It doesn't stop there. There's some fabulous images from the Juno spacecraft of Jupiter, in which you can see these, you're used to seeing the banded structure of Jupiter from high velocity winds that circulate around the planet, but there's also these large vortices associated with storms. They're all over the place. They're not just the Great Red Spot, but there's many of them. And when you look a little bit deeper in the atmosphere, you see these von Karman vortex pairs being generated by flows around these gigantic storms. I mean, a tremendously turbulent, complicated flow occurring in Jupiter's atmosphere that, again, if you want to understand the properties of Jupiter, you want to understand that dynamics in more detail. And as we go to larger scales, to the interstellar medium, this is an image.
Excuse me, are these storms continuing all the time, or is that like just a specific coincidence that you picked it up?
These storms, or so these storms are very long-lived. The Great Red Spot was discovered by Galileo in the 17th century, and it's still going strong. So there's one gigantic vortex on Jupiter, which has been there for several hundred years. These smaller ones come and go on sort of year to decade timescales. So there's a huge range of these phenomena and features.
Could I ask, on the sun, you had these little cells, right? That
yes,
you showed us earlier.
Cells.
Yeah, and so what sets the scale for those? Is the magnetic field play a role for that, or what?
Magnetic field does play a role in the convection, but otherwise it's sort of a geometrical constraints. The thickness of the convective layer and the density variation with radius in the sun kind of sets a scale, the scale height of the sun, basically. And similar to the Earth's atmosphere, there's a length scale set by the change in pressure with height. And so in the solar atmosphere, there's a scale height, and that scale height sort of sets this horizontal dimension. So it's not convection in a uniform fluid like a pot on a stove. It's convection in a highly stratified fluid where the bottom of the box is much, much denser than the surface layers. And the variation of density with height sets the length scale to the problem, which can
okay, thanks. Yeah, that's
right. So interstellar medium here there's gas clouds that are in between the stars. In fact, they're the material out of which new stars are forming. This is a star forming region called the Carina nebula. out of which new young massive stars are being formed. And these stars are now starting to light up their surroundings and light up all this plasma that's from which they formed. The most massive star in the Milky Way galaxy is Eta Carina, the star right here. And the radiation field from that star is ablating and evaporating all the material around it. It's about 100 times more massive than the sun and many orders of magnitude more luminous. And it's just sculpting the material around. So just amazing structure in this turbulent interstellar medium. And just to show that, if we just blow up this one little box here and blow it up in larger scale, you see this, a remarkable structure emerging. So this is, again, a very dense cloud of gas, so dense we can't see stars behind it. It's blocking all the light. And this gas is being irradiated by the new stars formed nearby, which is producing this radial spikes. That's gas which is just being ablated, evaporated off its surface of these clouds. Inside these clouds, new stars are forming, and we know that because when you look at infrared wavelengths, this is an optical image, but when you look in the infrared, you can see inside and you can see new stars forming in the interior. And when these new stars form, they generate high velocity outflows and jets as plasma accretes onto them. And you can see those forming here. There's a brand new star forming in the tip of this column here. It's produced this very narrow jet beam that's broken out of the cloud, and you see a shock wave as this ejected plasma propagates into the surrounding medium. And it's going both ways. It's a bidimensional flow, so there's a shock at both directions as it propagates out. And there's another one here. This very long linear feature, again, is a high velocity collimated beam of plasma produced by a newly formed star here, maybe only a few 100,000 years old, which is producing flows and shocks as it propagates out into the interstellar medium. And so if we want to understand star formation and the structure of the interstellar medium, we need to understand this plasma dynamics.
A question?
Yes.
You said it's very dense. What's the order of magnitude there?
So very dense in the interstellar medium means 10 to the 5 to 10 to the 6 particles per cubic centimeter. The atmosphere, for comparison, is 10 to the 17 particles per cubic centimeter. So it's 10 to the 11 orders of magnitude less dense than the Earth's atmosphere. But that's still very dense because the mean density, the average density of gas in the galaxy is 1 particle per cubic centimeter. So this is 1,000,000 times more dense than the average density of the interstellar medium. So in that sense, it's more dense, but on human terrestrial terms, it's still extremely tenuous, much better than any vacuum you can create on the Earth.
Thank you.
So another amazing example is the Crab Nebula. And I think it's amazing because it's sort of a direct demonstration of a classic fluid dynamical instability, in the sky, as it were. So this is a supernova, a massive star which exploded about 1,000 years ago at the end of its life. What you see mostly here is the outer layers of that star, which are being blasted into interstellar space. This is a much smaller scale image than the previous image I showed you before. This is maybe a few times the size of the solar system, this whole area. And the supernova generated what's called a pulsar in the center, a rapidly spinning neutron star. And this neutron star is energizing plasma around it. It's producing high energy particles, which are inflating a pressure-driven bubble. It's kind of like blowing up a balloon in the middle of the supernova remnant. And that's this white glow you see. The white glow is emission from the high energy electrons being produced by this rotating pulsar. So as this bubble expands, it sweeps up the surrounding ejecta, and you have a low density plasma, a bubble accelerating a high density plasma, the background material, and that's subject to something called the Rayleigh-Taylor instability. Whenever you accelerate a high density plasma by a low density plasma, that's linearly unstable, and you get fingers and drips. Classical analog is when you paint the ceiling, the air can't support the paint and you get drops falling down. That's Rayleigh-Taylor instability. And you can see these little fingers, these little filaments everywhere in this image, all over the place. There's these long droplets of dense plasma which are dripping into the center of this nebula because they're Rayleigh-Taylor unstable as you try to blow accelerate this high density ejecta by the low density pulsar nebula bubble, then you get this Rayleigh-Taylor instability. So that's kind of a fascinating example of classical fluid instability you can see in an HST image. And then it's not just our own galaxy, you know, external galaxies. They're all just plasmas. All those stars in this image, all the interstellar medium, these dense clouds, this dark regions are dense clouds filled with dust that's blocking background starlight. If you want to understand galaxies as a whole, you have to understand this plasma dynamics and how it forms stars, how it forms galaxies, and how it evolves. So the motivation is really broad and clear from all these images. So that's my little background slideshow of some of the highlights from you know, HST and other telescopes. So we have this motivation. All these objects are basically plasmas, and if you really want to understand how planets, stars, galaxies form and evolve, you've got to understand the plasma dynamics directly, and that sort of underlies what I do. So where would you start with that? What would be the, you know, what would you need to do to model the plasma dynamics? Well, the most fundamental description of plasma dynamics, as I'm sure you know, comes from the Vlasov-Maxwell system of equations, which describes the evolution of the phase space density F at every point in space and in momentum space and in time. You know, this is a partial differential equation given the evolution of the phase space density. Contains the sort of advective term, how the phase space density evolves due to fluid motion or plasma motion, and the acceleration term, how it evolves due to forces being applied on the particles in the plasma. And because these are charged particles, most of the forces is coming from electromagnetic fields, electric fields E and magnetic fields B. So they produce forces QE on and the V cross B force due to motion of the particle in a magnetic field. So you need equations to describe the evolution of E and B, and those are, of course, Maxwell's equations, which again depend on the plasma itself through things like the current density, which is nothing more than volume integrals of the phase space density and charge, wherever there's relative motion between charges, different sign charges, you get a current, and that'll generate magnetic field. And similarly, if there's charge separation, this is the mean charge density. If there's more charges of one sign than another in some location, you'll get an electric field, which will then feed back into the Vlasov equation. So you would need to solve this equation if you wanted to model the plasma kinetics from sort of first principles approach. But of course, that's very challenging, partially because this is a 7-dimensional PDE, the phase space here, three spatial dimensions, 3 momentum coordinates. And so that's very, very large. And moreover, there's very small time and length scales in this equation. You're resolving the plasma kinetics on the gyro motion of individual particles. You're following the individual motion of particles as they spiral around magnetic field lines. And you're following time scales which are shorter than the gyro motion of those particles. And so if you really wanted to follow this, you know, even if you could integrate the 7-dimensional phase space, you would, and you want to follow it for astronomical time scales, you know, it's just too challenging because of the range of length and time scales would just be intractable. And so while there are certain problems like trying to understand solar wind, Earth's magnetosphere, there are problems where kinetic effects, where following the dynamics of the collisionist plasma is very important. We have colleagues here at Princeton, at PPPL, the Princeton Plasma Physics Lab. They spend their careers, you know, doing magnetic confusion and trying to magnetic fusion, and trying to understand how to integrate these equations. These are important applications in astrophysics. Nonetheless, for a lot of problems, you can solve a simpler set of equations, which is, of course, by taking moments of this over the velocity coordinates.
Sorry, I have a question. When you say integrating these, you mean numerically or?
I mean, of course, analytically would be best, but the number of solutions you can find analytically is
so. But basically, then it's numerical.
It's basically numerics. Yeah. Okay. So you know, even at the lab, if you're looking at tokamaks, it's mostly numerics. Either numerics.
Just, also to understand, yet 7-dimensional. How many particles are there?
Well, in an astronomical flow, we would be talking, of course, about, you know, Avogadro numbers of particles.
Okay, right.
Which is, so one would never do that for each individual particle. In the end, you would use some discretization of the phase space, which would have some finite volume in phase space that containing some finite number of particles, and you would do it that way. But yeah, so even with that, it's a very challenging problem.
Right.
So really an attractive way forward is to basically integrate these equations over momentum, take moments, and that of course leads to the classical equations of fluid dynamics, to Euler's equations. Normally there would be a closure problem that every time you take a moment of this equation, you get terms which depend on yet one higher moment. But in a case where these plasma is collisional, if you're looking at length scales much longer than the particle mean free path, then on those length scales, the distribution function tends towards a Maxwellian. And then you can have an analytic closure between higher order moments. You have an equation of state. You know how the pressure depends on lower order moments like density and energy density. And so you have an analytic closure through an equation of state, and you can write down a closed system of equations. For example, the equations of magnetohydrodynamics, which are nothing more than Euler's equations, essentially, supplemented by Maxwell's equations in the limit of infinite conductivity for ideal MHD. And that's appropriate when you're looking at long length scales, long compared to particle mean free paths, a highly collisional plasma, which is fully ionized, so it has no neutral particles left, and you're looking at low frequencies, so long time scales compared to electromagnetic waves, for example, that might exist in the plasma. And then we're forced to solve this much simpler system, yet still complicated system of PDEs. And so this is the mathematical model that sort of motivates astrophysical fluid dynamics, the continuum approach for doing MHD.
And what's the mean free path here typically in things you study?
So mean free paths, of course, depends very much on the system scale.
Yeah.
But it might be kilometers.
Yeah.
And we're interested in studying things which are parsecs in scale, or 10 to the 12 kilometers in scale. So
yeah, so that's
scale separation is not a problem. And
no, it doesn't seem to be, yeah.
In that case. Now, if you're looking at things that are the size of the Earth, for example, in that plasma, you have to be a little more careful, where you're getting uncomfortably close, perhaps, to the collisional mean free path.
Is there a way to see, is there a way for gravity to get into the picture?
Yeah, so gravity would just enter as, a source term in here, and you would need to solve Poisson's equation in the Newtonian case, non-relativistic. So clearly these are the non-relativistic MHD equations for flows that are much less than the speed of light. If you want to do relativistic fluid dynamics, the equations can be written in a very similar form, in covariant form, and then relativity would be built in through the metric, through the space-time that you're evolving, and you could then consider general relativistic flows in which gravity enters through the curvature of space-time in some coordinate system with covariant equations. I didn't go into the full complexity of the general relativistic equations, but they're a very, very similar form. So gravity doesn't present any new particular challenge. It doesn't really add anything beyond an additional force to the right-hand side, if you like. So these are very, very familiar probably to many of you, because they're just, they're very much like the equations of terrestrial fluid dynamics. The only differences are the new terms due to magnetic forces, the momentum equation, the Poynting flux term, and the energy equation. And these are all for compressible flows. You really have to solve the compressible system of equations. So you can't simplify the continuity equation, for example. You need to keep the compressibility condition inside here. And of course, these are nonlinear hyperbolic PDEs. They involve first derivatives in time and space. And so you can rewrite them in this as a divergence of a flux, as they've already been written here. And you can rewrite that involving nonlinear hyperbolic PDE, where this Jacobian df du give you the characteristic speeds in MHD. So, as you know, probably the most important aspect of hyperbolic PDEs is they admit wave-like solutions. And in MHD, there are multiple wave families. And really, much of the dynamics associated with the fluid is associated with the complexity and the properties of the waves that are present. So let me give you a quick aside on MHD waves, if you're not familiar. But you know, you do the usual WKB analysis. You look for solutions of the form e to the I omega t minus kx. Look for small amplitude perturbations. You get a dispersion relation. In this case, for an isotropic, homogeneous, magnetized plasma, that gives you a 6-order polynomial, which can be factored conveniently into this form here. You clearly have one mode associated with the Alfven speed, this ratio of magnetic field to square root of density, basically. And notice that the Alfven speed's a vector. It depends on the magnetic field direction. So there's an anisotropic mode here. And then similarly, there's two modes with this term and this second square brackets, whose eigenvalues are a little more complicated, but they depend on Alfven speed and the sound speed in some combination. So the bottom line is that MHD has 3 wave modes, unlike hydro, which only has 1, sound waves. We now have so-called Alfven waves and both fast and slow magnetosonic waves. And, you know, again, almost all of the complexity of MHD comes from the properties of these MHD waves. And a very convenient way to look at this is through so-called Friedrichs diagrams. So these are basically polar plots of the phase velocity of different wave modes as a function of angle. So the vertical axis in each panel is parallel to the magnetic field, and the horizontal is perpendicular, directions perpendicular to the magnetic field. And the inner solid line is the slow magnetosonic mode, the dashed line is the Alfven mode, and the outer solid line is the fast magnetosonic mode. And each panel corresponds to a different ratio of sound speed to Alfven speed, so different magnetic field strength, because the Alfven speed depends on the magnetic field strength, so you can change its velocity just by changing the magnetic field strength. And without going through all the details, it's interesting just to say, look at the strong magnetic field case where this ratio of sound speed to Alfven speed is small. Then you have this sort of inner slow mode and Alfven mode. And notice that perpendicular to the magnetic field, there's only one wave that can propagate, the fast wave, whereas parallel, there's 2, only the slow and the fast mode. And the fast and the Alfven become degenerate. They're the same mode, parallel to the wave. At any other general direction, there are three modes. And which waves are degenerate depends on the ratio of the sound speed to Alfven speed. If you go to the weak magnetic field case, the Alfven speed's degenerate with the slow mode instead of the fast mode. And so this makes MHD much more complicated because the waves are anisotropic. They can be linearly degenerate. So MHD equations are not strictly hyperbolic because it doesn't have unique eigenvalues in all cases. And so solving them, you know, depends on direction and so on. It makes it much more complicated. And an even additional complication is the Alfven mode is polarized because it's a transverse wave. It involves vibrations of the magnetic field in the transverse direction. So 2 linearly polarized Alfven modes in 2 orthogonal directions can give you circularly polarized waves. Again, something that doesn't happen with sound waves, which are purely longitudinal. So you need at least 2 transverse directions, even in 1D for MHD. And so all of these complexities makes MHD much more complicated than just regular hydrodynamics. So with that flavor, I thought that I would tell you a little bit about the numerical methods that we adopt, because we sort of already mentioned, you know, finding analytic solutions to these equations, even to the MHD equations, let alone the Vlasov equations, is essentially impossible except for very simplistic one-dimensional or steady state flows. And so now astrophysics relies very heavily on numerical methods, in part because computers are so much faster, and in part because algorithms have gotten so much better. We have reliable algorithms that have been developed through very rigorous analysis for which we have, you know, rigorous bounds on their stability and convergence properties. I got to say something about faster computers, because this is a big part of this game, is that these are large, you know, we're going to be studying 3-dimensional time-dependent problems, and they're very expensive And so you need to be able to run on the largest computers in the world. Today, the largest computer in the world is a machine called Summit at Oak Ridge National Laboratory. It has 27,000 GPUs on it and 200 petaflops of performance. Takes about 13 megawatts of electricity. And in fact, that's the limiting factor in building bigger computers today, is this how much power they consume. It's really difficult to build something larger than this because the heat they generate is just too much to be contained within one building. So if you're going to run large realistic calculations, your software has to be able to run on these kinds of machines, meaning it has to run on GPUs rather than regular CPUs, and it has to be able to run on thousands of GPUs at once. And that's a huge challenge to developing the software that has to be faced, and it's an important part of the field. But really, the biggest development is not so much the computers, but it's in the algorithms. They're just way better than they were back in von Neumann's time. Another privilege of being here is, a lot of the pioneering work, not only in the algorithms, but in the hardware, of course, was done here at the IAS. And the algorithms that are used today, all have been built on the pioneering work of von Neumann and others back in the day, as it were, but they've gotten much better. So not only are computers a lot faster than MANIAC, they're also, the algorithms are just simply much, much better. And I thought I would give you a couple of slides on what we're using, so-called finite-volume discretizations, which are well suited for solving compressible problems. So in a nutshell, you discretize space into discrete volumes. You discretize the continuous variables into volume average values. So you integrate the continuous variable over the volume of each cell, and you store the volume average values of density, momentum, total energy, and so on in each position. You're not storing the point-wise values of these functions, but rather the volume integrated values of these functions. And then the conservation laws, the difference equations result simply by integrating these PDEs over a volume and then applying the divergence theorem to turn the integral of the divergence of the fluxes into the differences of the area integrated fluxes over the faces of the cells. And so this F at n plus a half, this notation means the time averaged flux integrated over the area of the faces of each cell. That's the quantity that you need to get to use an discretization. This is not an approximate formula. This equation is exact. If you have an exact representation for the time averaged and area integrated flux, then there's no error in this equation. It all comes down to approximating, where the truncation error enters is where you approximate this flux by some discrete form, and that's where the error enters.
Sorry, presumably it's the same technique is used in weather computations?
So we were just discussing this a little bit earlier, but in weather, you're mostly solving the incompressible equations. And there, things like spectral methods are preferred because you don't have discontinuities, you don't have shocks, for example. And spectral methods are very good at smooth flow. They're not so good when you have a shock wave where you have discontinuity. Representing that with some spectral basis is probably not a good idea. And so, so the fluid dynamic community, I think, is using methods that are related but not the same. I'll show you a comparison a little bit. So again, this is just sort of a summary. You store volume average values in the center of the cells. Magnetic fields are at the surfaces. And we calculate the fluxes, these F, G, and H, at the faces of the cells to update these conserved variables U at the cell volume centers by solving what are known as Riemann problems. I mean, it all comes from a pioneering paper in the 50s by Godunov, who pointed out one approach to solving these equations. He postulated, well, what happens if you just took, imagine a one-dimensional distribution of these conserved variables Q, in which in each cell you had a piecewise constant state. And imagine if you just took that at face value and imagine this was actually the spatial distribution of the fluid, sort of like a histogram of fluid inside each cell. And then you let it go and evolved it in time. What would happen? Well, at each interface, there would be a discontinuity, which would therefore define a so-called Riemann problem in fluid dynamics, the evolution of a discontinuous interface. And you can do that analytically. You can evolve the Riemann problem analytically, and you can calculate what the structure of the fluid flow would be at later times. So for example, if this were the pressure, this pressure jump would launch a shock wave to the right and rarefaction to the left, and you get this little structure inside this, emerging from this interface, and so on from each of the individual interfaces, you get this structure. And then at some later time, you just need to integrate this curve inside each cell, and you would know how the conserved quantities are evolving in time. And you can do this up until this shock wave crosses the cell and starts hitting this interface. Then you got to stop the calculation because now the shock, one interface is affecting the other one. And so you can only evolve this for time steps which are smaller than the shock crossing time of a cell. And this gives you a heuristic derivation of the CFL condition, the Friedrichs-Levy condition, which actually comes from more mathematical von Neumann stability analysis. You can show this directly, but here you can just on physical arguments explain the CFL condition. But what Godunov realized is that you don't need to know this exact curve here, which is very complicated to calculate. All you really need to know is the solution to the Riemann problem at the interface itself, along the line x equals the interface value. Because then from conservation, if you know the flux, if you know the solution along the dotted line, from conservation, you know that the solution inside the cell is just a divergence of the flux through the faces. So all you really need the Riemann solver to do is to calculate the value at a single location in space, not over the whole, space-time. And that's sort of the genius of the Godunov method, is all you do is you replace this Riemann problem in which you would calculate the exact spatial structure with just calculating the value along the line x equals 0 in this sort of space-time plot. Here's space and time, it's a self-similar solution. You don't care about the rarefactions and shocks, you just want to know what the value is at this interface along the line here. And if you can do that, you can then use conservation. And it's actually quite inexpensive to calculate the solution at this point. And so that's what we do. We use these Riemann solvers to calculate these solutions. And then when you know that, you can calculate these time average fluxes at the interfaces and then update the solutions according to the difference equations. And in MHD, it's what we do. For hydro, in fact, these Riemann solvers are not so expensive and you can implement exact solvers. But for MHD, exact nonlinear Riemann solvers are too complicated because, as I mentioned, there's 3 wave families, 7 characteristics, 6 potential intermediate states in the Riemann problem. And moreover, there isn't always 7 characteristics. Some of these waves are degenerate. So sometimes in some directions, there might only be 5 intermediate states, and be able to switch between them automatically is very, very complicated. And so instead, what people do is approximate or linearized Riemann solvers, which give you an excellent approximation to the intermediate state without solving the exact problem everywhere. And again, this works extremely well. It's not quite the end of the story because Godunov's scheme is only first order in space and time because you're only considering the internal structure as being constant. But in fact, what you do is you fit higher order polynomials to the internal structure of the cell, and then you use the left and right states given by these interpolation polynomials to solve the Riemann problem. And nowadays, typically people use 4th order reconstruction in space and 4th order so-called Strong's stability preserving time integration algorithms. So RK4 or RK3 integration techniques to make higher order methods. So you can get 3rd and 4th order algorithms in these finite volume methods fairly directly. And that seems to be good enough. That gives you excellent accuracy for smooth flow while maintaining stability. The beauty of Godunov methods is they're extremely robust for shock waves because they build in a Riemann problem directly to the solution. They build in the solution for the nonlinear shocks directly into the calculation of the fluxes. And so they're very, very robust at shock capturing. And so that makes them very attractive for compressible problems. And after all, whenever you have discontinuities, all methods are only 1st order anyways. And so 3rd and 4th order methods are actually pretty good as long as they're robust as well.
May I ask a question?
Yes.
So when you're saying they seem to be most effective, you mean that it wouldn't actually you wouldn't gain too much by going with higher order approximations, or is there something special, like, you know, that you see happening in this with these numbers?
Nothing special. It's a sort of a cost benefit analysis. If you go to higher order, does that really make the overall solution more accurate when you have first order error associated with all these discontinuities everywhere? And that's very much an application dependent question.
Mm-hmm.
There are certain problems, very low Mach number flows, very smooth flows, where I'm sure higher order would actually be a win. But in general, for, you know, complex supersonic turbulence, it's not clear, or experience seemed to show that sort of third order in time and fourth order space is the most cost-effective way.
But you're still better than third order in space and second order in time, say. I mean, so there's something interesting going on, which...
Yes, better than second order is definitely...
Because of course, shocks and discontinuities, are, as you're saying, they're always first order.
That's
so
right,
it's unclear why you stop at...
There's no sort of truth of where the sweet spot is. And I'm sure it's a problem dependent question. But sort of experience seems to show, quote unquote, that this is sort of the sweet spot.
Thanks.
Yep.
And could I ask about
a funny question? How do you know when it's working? So you get solutions.
Excellent question. Let me jump ahead to that. So let me also say that adaptive mesh refinement is very important, and we use that a lot. Let me just say very, very briefly, it's just a technique to refine the mesh where small scale features appear, and it's very important for the, you know, numerical infrastructure to implement this, but I won't say much more about it. And if you're interested in AMR, it's another very, very complicated and important, you know, topic. But let me just skip forward to your question, which is, how do we know it works? Well, we can go back to the linear wave problem. You know, we actually do have some analytic solutions. We know for linear waves what the solution should be, and we can use that to measure the convergence rates for each of the wave modes in MHD, the fast magnetosonic, the Alfven wave, the slow mode. We call the entropy mode, that's just advection. We call that the entropy, you know, another fourth wave family, the entropy mode. And you can compute, you know, basically you set up an exact eigenvalue, eigenvector of the solution, you evolve it on the mesh, you propagate the wave for a few periods, and then you calculate the L2 error by subtracting it off from the analytic solution, and you measure how that error changes with resolution, and that's the convergence rate of the method. And for here, we were using a second order method, and so we're getting, you know, nice second order convergence, and we can compare different second order schemes and measure the absolute error between them and determine which one is the most accurate, and, you know, quantitatively measure errors. You know, although this is still difficult because we don't have a whole lot of analytic solutions, you know, using shock tubes. There's analytic solutions for shock tube problems in one dimension. We use those as well. But some of the most interesting comparison comes from cross-code comparisons. So here's an example of a calculation of the the Kelvin-Helmholtz stability. So again, that's the classical fluid instability where you have two fluids streaming past one another with a resolved shear layer in between them. And you then perturb the interface, and that's linearly unstable and generates an exponentially growing mode for which you can compute growth rates analytically. But moreover, you know, if you add explicit resistive or explicit viscosity to this fluid dynamical problem, you can compute converged solutions at finite Reynolds number using things like spectral methods. So this plot shows you the evolution of the Kelvin-Helmholtz stability at 4 different times, and each vertical column corresponds to a different code or a different resolution. And this D4096 is a spectral method with 4096 squared spectral elements and should be considered the exact converged solution for this problem. In other words, if you add more spectral elements, you don't change anything in the solution. And then you can compare this to this finite volume method using a third order integrator, fourth order in space, using 4096 squared cells. You can see there's slight differences, but very slight. And you go to 88,000 squared cells, and it's almost exactly the same. In fact, we can take the finite volume solution, subtract off the spectral solution, and calculate the L2 error, and it's extremely small, 10 to the minus 5, even when it's gone into this nonlinear late turbulent regime. So it's converging exactly to the spectral solution. And so it's another way of cross-calibrating. But what's interesting is that it only costs half as much as a spectral solution. So remarkably, you can get spectral accuracy with these methods for much less cost than a spectral code. Spectral methods are the gold standard, but I wonder whether or not they're really always that, whether or not isn't better. I mean, it's the same answer, but I only use half the number of computer cycles to get it. So I'm okay with that.
Yeah, it's convincing.
So again, we spend a lot of time trying to validate these methods through classic fluid dynamical instabilities and analytic solutions where we can find them.
Yeah, I was going to ask about the shocks themselves. Now, these are surfaces, I suppose, right?
The shocks?
Yeah.
Yes. I mean, surfaces.
So how accurately can you actually get the structure of the surface? I mean, or you don't just suppose it's a hyperplanar, do you?
So that's a very good point about when you're representing a surface in three-dimensional space, then there's inevitably discretization error in trying to represent that surface. In fact, if you make the shock too thin, you get stair stepping on a finite mesh, and that's bad because that introduces power in the transverse direction of the shock wave, which can introduce new dynamics that wasn't there. Basically, grid noise can seed in fluid dynamical instabilities that shouldn't be there. And so, in fact, there's actually reason to not want to make shocks just one cell thick in multi-dimensions. Yeah, it's another technical area that we could discuss, but there is some sweet spot where you don't want to do that. So these shock capturing methods, we don't do anything special. The shocks emerge, automatically from the method itself. And so we don't worry about trying to do anything special. There's not sort of any kind of, James Glim has these surface tracking methods for interfaces. We're not trying to do anything like that. The shocks just emerged directly from the flow. And again, these methods are really good on parallel computers because you can do domain decomposition, and we get essentially perfect weak scaling up to 500,000 computing elements, which is about the bigger computers you can get nowadays. So these methods work extremely well. Another advantage over spectral methods is that they work extremely well on parallel computers. So I only have 10 minutes left, but maybe bear with me, maybe I'll show you a little bit of results. So one motivating result is trying to understand black hole accretion. And one motivating observation is this, I'm sure you've all heard, the first image of a black hole generated by the Event Horizon Telescope. It looked at the center of a galaxy called M87. And at the very, very tiny scales at the center of M87, we know there's a supermassive black hole. And the projected area of the event horizon of that black hole on the sky is just big enough to be resolved by a telescope the size of the Earth. And by doing interferometry, we can build a telescope the size of the Earth by connecting telescopes at different locations on the surface of the Earth, and we generated this image. And the hole in the middle is the shadow produced by the event horizon. So we can actually measure the physical size of it and infer the mass of the black hole and other properties from this image. But after all, it's a black hole. It's not generating light. Where is this emission coming from? It's coming from plasma that's accreting inwards into the black hole. And if you want to understand the emission, you got to understand plasma accretion onto a black hole. It's a fundamental. I mean, the black hole itself, in vacuum, you'd see nothing. And so without this plasma, you wouldn't see this image. And so understanding this plasma dynamics is crucial for interpreting these kind of images. So that's the challenge. Where does this plasma come from? It comes from, well, there's a black hole at the center of the Milky Way, just like M87. And we know in that case, in the case of the Milky Way, it comes from stars that are very close to the black hole, orbiting very, very close in. How close in? So this picture here is 25 parsecs across. The galactic center is 8,000 parsecs away. So this is a tiny little volume 1,000 times farther away than this image here, showing the galactic center. And then at the point of that arrow is the size of this image here, showing you the motions of stars around the black hole in the Milky Way over the last 20 years or so. These stars are gravitationally bound to the black hole, and they also are producing winds, just like the sun has a wind. And those winds collide with each other and generate plasma around the black hole. And that's the plasma that's accreting inwards in the Milky Way. And similar things are happening in M87. And we can actually model this directly. We can take these compressible fluid dynamic models. We can evolve the motion of the observed stars around a central point mass. And we can follow the winds as they collide with each other. And it generates this turbulent flow around the galactic center. That's what this calculation has been doing. And from these calculations, we can measure the density and temperature of the plasma in the region surrounding the black hole at the galactic center. And when you zoom in, so this has been evolved for about 10,000 years as these stars orbit around. If you zoom into the very central region, now things are much accelerated because we're looking on very, very small scales. What you see emerging is a rotating disk of plasma around the central black hole. It comes and it goes as stars go by and their winds blow into this cloud of gas that's rotating around the black hole, but there it is. And that's what's feeding the black hole at M87 as well. So it turns out what we need to understand is the dynamics of disks of plasma around black holes. And their magnetic fields come back again because it's known that plasma, which is in orbital motion around a central object, is unstable to an MHD instability called the magnetorotational instability. It's very much like other classical instabilities like Kelvin-Holmes and Rayleigh-Taylor. It comes from just straightforward WKB analysis of linear waves. So Alfven waves are linearly unstable in this circumstance. I had a whole slide on it, but in the interest of time, I think I'll skip it. But from a WKB analysis, you can derive the linear properties of this instability. And then using numerical simulations, we've been studying the nonlinear regime of this instability. So here's an image of a disk around a black hole. Imagine taking a little postage stamp, a two-dimensional plane here, and evolving the MHD equations in this little area here, not the whole disk, just one little small volume. Evolve the MHD equations, you're going to see this magnetorotational instability. So you put in small linear perturbations, and boom, you start seeing these coherent waves emerging. These are the exponential amplification of Alfven waves. They then grow nonlinear, and then they saturate into turbulence. And so using these computational methods, we've understood that the MRI saturates as MHD turbulence, and we've been able to measure the properties of this turbulence. For example, this turbulence transports angular momentum. It generates effectively a viscosity, and this viscosity transports angular momentum and is what drives matter inwards, because without angular momentum transport, you can't get matter flowing inwards towards the center. And so through the last 20 years of sort of MHD studies, we've been looking at the nonlinear regime of MHD turbulence using these computational methods. And that's what we need to understand the dynamics around this black hole. So, here's sustained turbulence driven by the MRI in these local patches. So we can go back now and we can redo the inner sort of 10 Schwarzschild radii around the black hole. Remember, we went all the way from 1 parsec scales, 10 to the 5 gravitational radii, and now we've zoomed all the way in down to the last 10 gravitational radii. Here's a torus of plasma. This is a poloidal slice through a 3D calculation. Here's a torus of plasma rotating around the black hole. If it's magnetized, it's unstable to the MRI. As soon as the MRI grows, it generates turbulence and accretion. It also generates winds and outflows, and we can evolve this to steady state. And then we can use this plasma dynamical model to compare to the EHT images now. We can now that we know the plasma density and kinetics around the black hole itself, we can now create a synthetic image of this. It requires GR ray tracing. So one more complication is that, you know, GR light bending is very important at the scale of the event horizon. So if you have a disk of plasma around a black hole, so the red black thing is the event horizon, if you like, and the blue is, imagine a plate, a thin accretion disk around a black hole. Well, it wouldn't look like it does in the case of Newtonian dynamics like Saturn. Because of light bending, you can see the back, you know, light rays emitted by the back of the disk travel up and get bent by the black hole. So you can see the back of the accretion disk over the top of the black hole. And that's a very important effect for modifying the image. So you've got to incorporate all the relativistic ray tracing to compute an actual image. But people have done that. They've taken the plasma simulation I showed you, they combine that with relativistic ray tracing, and they compute a series of images where you tilt the axis of the accretion disk at different angles relative to your line of sight, and you compare it to what the EHT image looks like, and you find the best fit. So for example, 90 degrees here is ruled out because you don't get a fit, you know, a hole in the middle when it's 90 degrees. If you're looking face on, you don't see it. So you know that the disk has to be tilted by some angle. And so that's sort of the end of the story. That's how we use these computational methods to try to interpret EHT. And this is a very qualitative description. In reality, we can use the intensity, time variability, and so on to measure quantitative properties of the black hole, like its mass and spin and other properties. But it requires knowing this plasma dynamics to be able to do all of that. So let me finish up by telling you that, you know, we're not done. There's a lot more physics. Ideal MHD is a great start, but we do need to worry about collisionist plasma effects, and radiation transport I've highlighted as being one thing that's really important as well for some problems, and incorporating radiation transport is going to be very difficult for the future, but it's an area for the future. I wanted to mention one area, which is more accurate algorithms. And while we think these higher order methods are great, you know, we're always open to new novel methods. And I don't know if this is being thought about in the math community, but there's considerable interest in, you know, machine learning. It seems to be everywhere. Here's a paper out of Google Research in which they claim you can solve the Navier-Stokes equations with machine learning. It's remarkable. Here's a direct simulation, 2000 squared, of the Navier-Stokes equations in 2D, showing the evolution of vorticity in a driven turbulence flow. And they sort of highlight one vortex which appears during this time period that they've just selected by hand. If you do this simulation with only 64 squared spectral elements, you don't see that vortex persisting. So this is not enough resolution to see that. But if you do it with 64 squared plus machine learning, then remarkably, they get very good correspondence between the actual solution you expect and this machine learned solution. Problem is, I have no idea what this machine learning is doing. I have no idea if this is right or wrong, but the images look similar. There needs to be a more quantitative way of measuring the accuracy and fidelity of these kind of methods. But will these methods work for doing turbulence? I don't know, maybe. I mean, maybe there's a way that you can machine learn subgrid models and put in subgrid models for turbulence. This is done in aerospace industry all the time to represent small scales that are not resolved in your simulation. If so, that would be great. But I don't know how to do it yet. But we're very interested. And so this is the kind of research in the future that I think would be very interesting to pursue. I have no idea whether this is going to work, but it's kind of very intriguing. So we're interested in more accurate and novel algorithms. And we're interested in trying to understand turbulence and MHD and radiation hydro. It's different than classical Kolmogorov turbulence. People are still arguing about the power spectrum of MHD turbulence. Is it 5/3? Is it 3/2? We don't know. And so there's basic fundamental questions in turbulence that I don't think are fully answered. And then finally, you know, these can be applied to many other problems. So, and I won't say anything more, but again, there's just many, many applications of these methods elsewhere. So I've run over a little bit. I apologize. So let me quit here.
Oh, thank you very much. It's an extremely interesting lecture. Thank you.
Sure.
But I'm sure there are a lot of questions.
With the Google papers from what period?
It's like a month ago.
Do you know that we have some potential collaboration with machine learning people at Google who you might want to?
I mean, I knew there was various efforts, and yeah, but are they working in CFD or are they working? I mean,
maybe Camilla knows, because Camilla, are you there?
Yes, I am.
And didn't you discuss some problems with them, which I assume are
yeah, but I don't know if it's the same Google people, right? I mean, like
secrecy.
No. Like, yeah, not yet actually. So, but the people we were talking to are the people at DeepMind. I don't know if it's the same crowd actually that is doing that. So, because when I asked them, I mean, the people that we talked about, that we talked to were people who are like interacting with mathematicians, with pure mathematicians, trying to understand them. And I asked them if they had done anything like, you know, in analysis or PDEs, and they told me no. So. Unless they're just, you know, sworn to secrecy at the point that they can't give me a straight answer.
Right.
Right. Actually, coming to this, do you know exactly what they learn? So when they're saying that they're using machine learning, with
I should.
So how do they train the network, right? So because because the network needs data before, right?
That's
so
correct.
It must be trained on something that are data. So
so they run this DNS, you know, hundreds of or thousands of times, and they train it on that data using different initial conditions and different forcing functions and different Reynolds numbers. And then they build this network into the actual integration algorithm itself. They're still solving the fluid equations, but they're solving them on a much coarser mesh with some kind of, you know, so they're only really solving the vorticity equation, because in 2D incompressible, you can reduce it all down to that. So then there's basically a forcing function on the vorticity that's coming out of machine learning, which I have no idea what it is, but there's some kind of, you know, fluctuations being added at every time step by the machine learning, which is required to reproduce the structures that you see. I can send you the link if you like.
Thank you. So, but let me get this correct. So first of all, they make a simulation with the like tighter mesh, a lot of them, and they feed it to the
yes.
Okay, and then they actually do the computation on a like less, I mean, on a much coarser mesh.
Yes.
And the neural network actually decides to correct that with some forcing and to get it better. But I mean, but now, of course, the provocative question is that you train them on the computation on the larger mesh, actually on many of them. So is it really effective at that point? Because you had anyway to use the simulations for to create lots of data, right?
Of course, it's the cost of training, but you know, I think they would argue, well, once you've done it once, you can now solve any problem in fluid dynamics for the rest of eternity, and so that saves you time.
Well, okay, if it's really that useful on other data, though.
So the question is precisely that. You now look at some other problem. Does it work, or is it only ever being? I mean, this is a very. My complaint is this is a very symmetric problem. It's 2 dimensions, meaning that, you know, the turbulence behaves differently, right? In 2D,
sure,
cascading upwards, not downwards. So if you do this in 3D, it doesn't at all obvious to me that this is going to work in 3D, where the cascade works the other way. And if you solved it, I mean, imagine doing the Kelvin-Helmholtz instability now. Forget about these driven turbulence problems. Just do a classical fluid instability problem with it. Would it give you the right answer? You know, can you test it in the same way we test our codes?
Yeah, they don't do that. They don't address that in the paper like you did. I mean, you were very convincing when I asked that question. They don't.
No, I mean, they only just show you this kind of result, which is again very unsatisfying. But you know, but on the other hand, maybe it works. I don't know. I mean, I don't understand enough about machine learning to know whether. I mean, it seems to me that the one area of possible application would be in subgrid modeling. If you could somehow train on a large data set of turbulence simulations, maybe you could come up with a subgrid model that would work for modeling, MHD or something else. And that would be very exciting. But yeah, I think there needs to be more fluid dynamicists working with these machine learning approaches to sort of, because I feel like there's a lot of machine learning and not so much fluid dynamics in this.
Yeah.
Is Waynon doing something of this along these lines, or?
He was doing molecular dynamics, as far as I know, where, he was learning.
Yeah, no, I know. Yeah.
That's the only stuff I know he was doing.
I
don't know if he's doing CFD. So,
yeah,
I mean,
I think there's a paper by some of the same authors that does 3D too, right?
that I don't know. This is the only one that I know about from.
I mean, we had as a member, one of our members was Waynon's.
Oh, okay.
Working with.
All right.
Okay. That was last year, I think. You remember, Tom? I forget his name.
Who was that? Somebody working with Waynon?
He was part of the machine learning group, a co-worker of Waynon, who was quite opinionated about these things. Yeah.
There's certainly a lot of hype about this. I just like to know whether or not there's lots of meat here too or not. I just don't know.
And do you you mentioned many people from Courant Institute. Do you interact a lot with them?
I learn a lot from them. I am not working directly with lots of people from there, but we are happy to adopt all these new techniques that have been coming out of Courant and other places the last 10 or 15 years or so on high order methods and so on. Much of our emphasis is on adding an extra physics. A lot of these techniques are developed strictly for fluid, for hydrodynamics. Getting them to work in MHD can sometimes be a bit of a challenge. I think a big frontier is radiation hydrodynamics, which is yet another whole colloquium, because again, the equations are even more complicated, and there are new degrees of freedom and new wave modes that emerge. And so I think that's going to be a big area for the future.
But with these black holes, isn't there some kind of radiation there that emerges from particles moving into the black hole? Or
absolutely. So and that's what we see. That's what that image is made of. Is from the
you also need some kind of you mentioned this. You also need some kind of viscosity, right?
Yes. So the turbulence itself generates angular momentum transport, or a stress, a turbulence stress, which then generates the accretion, mass flow inwards and accretion. And because there's a stress, there's dissipation, and that dissipation produces heating, and that produces the photons that you see. If the mass, in the case of M87 and galactic center, where the HT is observed, the mass accretion rates are extremely low. And so the heating rate and the temperature reached by the plasma is relatively low. And so the radiation field has a non-negligible effect, but it's not dominant.
Mm-hmm.
But we know of black holes in the universe that are accreting at much, much higher rates. These are so-called quasars. The most luminous sources of radiation in the universe are accreting black holes. And for those sources, the radiation field completely dominates. It's a million times larger than the internal energy density of the plasma, for example. The energy density in the photons is completely dominant. And so modeling that regime of accretion requires a different system of equations than what I've shown you here, and is much less mature, because our numerical methods and our understanding of the physics is less well developed in that regime, but it's a very important area for the future.
So coming to that viscosity that you were mentioning, just if I understand correctly, so the viscosity is actually not in the equations, right? So the equations are non-viscous. So the viscosity that you're seeing is really the one that the turbulence is creating, like some Reynolds stress, which is created by that.
That's exactly right. So I should be very careful. It's not viscosity.
Yeah.
It's an effective viscosity.
It's an effective viscosity.
Yes, yeah. And in many ways, it doesn't behave like a viscosity. It's not proportional to the gradient of the velocity, for example. It's
wonderful. I'll cite you. I mean, that's why people criticize some of my work, that I can actually show there's some type of viscosity like that is appearing, and they complain it's not coming from Navier-Stokes. Well, it actually does happen in
absolutely
in real life.
Right. I mean, this magnetorotational instability and the understanding that MHD turbulence generates angular momentum transport has been revolutionary in astrophysics. It solved one of the most long-standing problems. The original authors, Balbus and Hawley, have won all sorts of prizes, Shaw Prize, so on and so forth, because this work, a simple linear stability analysis of an MHD fluid, it revealed this amazing, the simple results are always the best. And, it's hard to argue with the linear instability, and then the simulations showed how important it was in the nonlinear regime. It's been very, very interesting.
Well, maybe we'll stop here, but if you can hang around for a while for more questions. But I'd like to thank the speaker again for a fantastic lecture. Thank you very much.